at this point would be, as we have seen before, G1 times K plus T antenna plus T1. The second amplifier, if we relate it in the same way as we have done before to the input of this, then the noise density at this point would be G1 times K plus T antenna plus T1 plus K T2. And when we relate that again to this as a reference point, then we have to divide by G1. And then we have K times T antenna plus T1 plus K times T2 divided by G1. And this a physicist, American physicist, I believe with Danish origin, called Mr. Fries, II, has developed this formula. So basically, the system temperature, if we have a cascaded chain of amplifiers plus an antenna at the input, so the system temperature will be T antenna plus T1 plus T2 divided by G1. And sometimes the noise figure is given, and you can always calculate from noise figure to noise temperature. Noise temperature, if you have the noise figure, is F minus 1 times T0. T0 is the ambient temperature, reference temperature of 290 Kelvin, 20 degrees centigrade, roughly. So, sometimes we have not only amplifiers, but we have lossy lines somewhere in between, by definition. I mean, when we combine something by a cable, every cable has some loss, some more, some less. If the loss is defined as the input power versus the output power, I could also say this is 1 divided by G, gain. Then the temperature of this system would be the temperature of the source times L minus 1. So if the network is a resistor at T0, then the loss is identical to its noise figure. And we can calculate the temperature of the lossy line as L minus 1 times the reference temperature of 290 Kelvin. And this has an important impact, as we will see in a moment. So now let's assume we have this cascaded system, an antenna, a bit of cable up front of the first amplifier, and the second amplifier. So the system temperature, according to the Fries formula, will be antenna temperature plus the temperature of the lossy line. And then we have seen in the other formula, the next system comes in with its noise temperature divided by the gain of the previous. But the gain is now 1 over L. Yeah? So we multiply L times T1, and this is an important impact. Even if this is a low number, but if the loss is high, then we spoil the system temperature significantly. However, then for the next systems is L times T2 divided by G1. This is the gain of this one. However, if the gain of this one is very high, then this term is small, or can be small. So, when we look at this formula, we can derive some important design criteria. First of all, make this as small as possible, because then this is more or less, I mean, this can't be less than 1. Yeah? But then this would be dominated by the noise temperature of the first amplifier. And therefore, we have to select for the first amplifier, the so-called low noise amplifier, something which is as good as possible. I mean, this is a price impact, because an amplifier with a low noise temperature costs more than a not so well-performing one. So, just to give you an example, let's assume we are grabbing 150 Kelvin by the antenna. So for instance, the spacecraft looking at Earth, if it's a geostationary satellite with a narrow beam, then the satellite antenna will see practically the Earth. And the average temperature of this is 290 Kelvin, which means we can't do any better than 290 Kelvin in this case. I mean, with a small satellite in LEO, the antenna will only partially see the Earth, and the rest will be see the deep space, so we get less. So just an average figure, depends also on the angle of attack, etc. Let's say 150 Kelvin. And then we assume the low noise amplifier in our spacecraft is 200 Kelvin. The gain is 25 dB. The second amplifier has a noise figure of 8 dB and a gain of 40 dB. And then up front, we have a lossy line, piece of cable with or filter or whatever, with 1 dB loss. So when we insert that in our already known formula, by the way, if I should be too fast, then, I mean, just slow me down. Yeah? Raise your hand and say, this is way too fast, slow down. Am I too fast? Okay. So first we calculate the noise contribution by the lossy line. This is L minus 1 times 290. Careful. We have to make the anti-log, because when it's expressed in dB, we have to make it into ordinary numbers. So this is then, the anti-log is 10 to the power of the loss divided by 10, 1 dB. So it's 10 to the power of 1 over 10 minus 1 times 290, so it's 75 Kelvin. So 1 dB is not very much. This already contributes significantly, 75 additional Kelvin. Here I just calculate what is the noise contribution, because this was given in noise figure, so 8 dB. So we make the anti-log, 10 to the power of 8 divided by 10 minus 1 times 290. So this one has a noise temperature of more than 1500 Kelvin. Yeah? So which means if I would take a resistor with the same impedance, say 50 ohms, then I would have to heat up this resistor to 1500 Kelvin, so that will be very hot. It will evaporate at this temperature. But this is due to transistor effects here, this temperature. So then our system temperature would be 150 Kelvin coming in from the antenna, plus 75 Kelvin from the lossy line. And here, 200 Kelvin is our LNA, but this increases by the loss. 10 to the power of 1 over 10 is 1.258. Yeah? So this increases by a factor of 1.258. Yeah? And then again, we multiply this second amplifier divided by the gain of the previous one. But since this is a fairly high number, then this term is not so high. Overall, we get a system temperature of 483 Kelvin. Yeah? So this is more than twice as high as the LNA. Yeah? So once you think, hey, I have a wonderful LNA with 200 Kelvin, but a lot of other things come in. And in the end, you think, wow, my link budget doesn't work. Second example, I have now put this lossy line in between the first amplifier and the second one. Yeah? Basically, the message is bring your preamplifier immediately to the feed point of your antenna. Avoid losses in between. Not always possible, but that's the design goal. So then we have this formula here, antenna temperature plus T1 plus the temperature of the lossy line. But this becomes very small now because the gain of this may be high. And this, again, will be a small term. So let's see what we get. 356 Kelvin. Yeah? Much, much better. And now we make just a thought experiment. Same configuration as before, but we just switch the two amplifiers. Put the bad one up front and the good one here. The overall gain is obviously the same. But when we insert in this formula now, we get a horrible result. System temperature, 1670 Kelvin. Yeah? Just by having swapped the two amplifiers. So this is no good. The conclusion here is avoid losses up front of the low noise amplifier. Second, use an LNA with the lowest possible noise figure, and use a low noise amplifier with the highest possible gain. So The satellite antenna noise temperature, so it will grab noise from Earth. It will also grab some noise from outer space. This is also an observation. The oceans radiate more noise than the land masses, but on average, we can take the noise of the Earth on average conservatively 290 Kelvin. So here now just an example. Let's assume we have an omnidirectional antenna, 0 dB gain. On the spacecraft, our system temperature from the previous example, 483 Kelvin. So then the figure of merit would be 0 minus 10 log 483 is minus 26.8 dB per Kelvin. Yeah? So here I've assumed a very small satellite with an omnidirectional antenna. Just in comparison, a modern telecommunications geo satellite has some +4, +10 dB per Kelvin gain because of quite high gain antennas on board. Yeah, but here we have practically no antenna gain. So now let's calculate the signal to noise ratio. And the figures are, we are at UHF band, 70 centimeters, transmit antenna gain 18 dB, transmit power 10 watts, equivalent to 10 dBW, distance between ground and spacecraft, 1,000 kilometers. Our figure of merit of the spacecraft is minus 26.8 dB per Kelvin, and we are assuming here a bandwidth of 200 kilohertz. This is equivalent to 53 dB hertz. And now, when we insert that in the formula, which you already know, here signal to noise ratio is 28 dBW minus free space loss plus figure of merit, but the figure of merit is negative. Then minus 228.6 dB joule per Kelvin. This is the Boltzmann constant minus the bandwidth. So this ends up at very healthy 31.5 dB signal to noise ratio. So this is plenty. So what it means, we could happily reduce the transmit power. We can play around with the Excel sheet later. So we could reduce the transmit power here, or we could increase the bandwidth happily. C over N naught, this is normalized to 1 Hertz noise bandwidth. So the bandwidth doesn't show up here. So C over N naught would be here 84.5 dB hertz. I mean, this is useful if you play around with bandwidth. So you take this result from the link budget and then you just subtract the bandwidth is expressed in dB hertz, and then you have got the signal to noise ratio, power ratio. Okay, so far we have just considered the free space loss, but there are other losses as well. So first of all, polarization loss. I mean, any antenna has polarization of some sort, can be linear, can be circular. And if there's a mismatch between the polarization of the ground station antenna and the spacecraft antenna, then we have some additional losses. If transmit and receive are both circular, then, I mean, we have in theory no loss. Another loss is the pointing loss. So any antenna has a certain characteristic. So the lobe will have the maximum gain at bore side, and when we roll off here, it's getting less. And if now ground station antenna and satellite antenna are misaligned, then we get additional losses. So depends on how well you are aligned. Usually this is not that high. Yeah? However, I mean, with amateur radio ground stations, you typically have quite low-cost rotators, and the cheap ones have a pointing accuracy of about 3 degrees. If you have now a quite high-gain Yagi antenna, the half-power beamwidth, or if you have a dish, then the half-power beamwidth is in the same order of magnitude. And then if the tracking has not got the proper resolution, you will have some pointing loss there. Yeah? Then we have atmospheric attenuation. There's gaseous absorption in the atmosphere, and basically the physical effect is that there's an interaction between the water molecules and the electromagnetic wave. Yeah?